So now that we've seen the fundamental trig limit, we're now ready to start applying our knowledge of calculus to trig functions. In 7.4, we're going to concentrate on just two of them. We're going to concentrate on the sine and the cosine functions. These are by far the two most important functions in trig and a good place to start. So let's start with the function f of x equals sine x. So just a bit of a review for you. The graph of sine x would look something like this. If this was our function value, f of x, and this was our value of x, then what we do when we graph trig functions is we mark off our intervals according to our trip around the unit circle. When you travel around a unit circle, you start at 0 rads right here, and then you rotate through pi over 2 or 90-degree intervals. Those 90-degree intervals, or we're working in rads, pi over 2, would indicate each of these increments on our graph. So this would be pi over 2, this would be pi, 3 pi over 2, and then back around the full circle. After 2 pi, the function just repeats itself over again. So what a sine graph looks like is it starts at 0, 0, the sine of 0 being 0, and then at pi over 2, it rises up to a unit of 1. So this would be 1 unit. And then at pi, it comes back down to 0 again. And that's what you get when you travel around a unit circle. As you change the size of the angle, sine is the y value. So your y value starts at 0 and then climbs all the way up to 1. This is a unit circle. And then as you progress into quadrant 2, the value of y just starts coming down again until finally back to 0. So what the graph does is it comes up like this and drops back down. And then as you travel down into quadrants 3 and 4, it just repeats itself, except it heads in the negative direction. So this would be the graph of a sine wave over one cycle or one period. Now the graph doesn't end. If you were to travel around the circle a second time, the graph would just continue that way. And if you were to back up and go the other direction, the graph would head off in that direction. But, you know, there's no point, you don't want to draw the sine wave forever, so what we usually do is just draw one period of it. Now, of course, in a calculus class, we're interested in slope of tangents. We're interested in what's called a derivative. Obviously, this graph has tangents. If you were to pick a point somewhere on this graph, there would be a tangent line. You know, pick a different point right here, there would be a tangent line. And in calculus, we're interested in finding the slope of the tangent line, called the derivative. So what we're going to do is we're going to develop the derivative of sine x. Now, I think it's important that I'm not going to hold you responsible for actually proving or developing the derivative, but I think it's kind of important or neat to see where it comes from. So what we're going to do here is we're going to find the derivative f prime of x of the function f of x equals sine x. So to do this, we have to actually go back to the very beginning of our study of calculus, to the definition of a derivative. It's been a while, but the definition of a derivative, we hardly ever use the definition anymore now that we have all of our rules, but every once in a while we come across new functions that we don't have rules for, and we have to find out their derivatives, and we do that by always going back to our definition. The definition of a derivative is the limit as h approaches 0 of the secant slope, a function at x plus h minus the function at x all over h. We haven't seen that since back in the beginning of chapter 4. So there is our formula for a derivative. Now we just need to apply that formula to our sine function. So our derivative would be f prime of x would be the limit as h approaches 0. And then we have to plug x plus h into our function. So we would get the sine of x plus h. Then we have to subtract the function sine x all over h. Now, whenever you're faced with a limit, you know, we always want to try plugging in the value, but you'll notice that if you plug 0 in for h here, you'll get sine x minus sine x, which is 0 over 0. This is called the limit of indeterminate form. We spent a lot of time back in the earlier chapters studying limits of indeterminate form, but they were all algebraic functions. Now we have a trig function, and we need to somehow find this limit. So we're going to do some rearranging. We're going to use another identity from trig. It's called an addition identity. If you have the sine of an angle plus an angle, which is what we have right here, that can be expanded. That's going to be the sine of x times the cos of h plus the cos of x times the sine of h. I'm just using there an identity. You may have to, again, refer to an identity sheet. That's called our addition identity, or some people call it a sum identity. Then we're subtracting the sine x, and that's all being divided by x. This limit is still indeterminate, so we're just going to do some rearranging. I'm going to put all the terms together in the following way. So what I'm going to do is I'm going to take this sine x cos h, this term right here, and I'm going to combine it with the last term, the minus sine x, and that's all being divided by h. Plus, and then I've got this middle term, cos x sine h all over h. So all I've done there is some rearranging. I haven't done anything other than just, all of these terms are being divided by h, so I've just rewritten how they're, rearranged how it's been written. Now what I can do is I can take out a common factor. There's a common factor here of sine x. So if I take the common factor out, I'll get that. Sine x times cos h minus 1 over h. And over here, I'm going to isolate this cos x as well by pulling it out and just writing this as sine h over h. Now recall from the previous section, there was what was called the fundamental trig limit. And the fundamental trig limit said that the limit as h approaches 0 of sine h over h is 1. That was our fundamental trig limit. And then one of the corollaries that we developed from that was the limit as h approaches 0 of cos h minus 1 over h is 0. Well, you'll notice that both of those limits now appear in our derivative. And that's why we looked at those limits in the previous section. So our derivative f prime of x is equal to, we can now take the limit. When we take the limit, all of this right here becomes 0, and all of this right here becomes 1. And we end up with sine x times 0 plus cos x times 1. Of course, sine x times 0 is just 0. And we've now developed our very first derivative of calculus, or derivative of trig functions. We end up with f prime of x equals cos x. It's kind of an interesting result. What it says is that the derivative of a sine wave is a cos wave. So just to summarize, so this is our first rule. There'll be 6 rules altogether in this unit because there's 6 trig functions. Our first rule says, if you have a function f of x equals sine x, then the derivative f prime is just equal to cos x. Okay, now that we've seen that we can take the derivative of sine x, let's actually have a look at what that means. Maybe a picture would help you understand this a bit better. So we've seen that if you have the function f of x equals sine x, and I've just drawn the picture of the graph for you again over one cycle. We know that if you have a function f of x equals sine x, that the derivative f prime we developed was equal to cos x. So what exactly does that mean? So what I've done here is I've asked the question, find the slope of the tangent line to our sine wave at the following points. So we know the derivative is cos x. So let's look at our first value. The question says, find the slope of the tangent at x equals 0. Well, x equals 0 would be this point right here at the origin. The tangent would be the line that just touches the graph like that. Now we know that a tangent is a derivative. So the tangent is going to be the slope at f prime of x when x is 0. So we're just going to go f prime at 0 is going to be the cos of 0. Now remember, we're in rads, so if you're using a calculator, just put it in rad mode and type in the cos of 0. The cos of 0 has a value of 1. So if you were to draw a tangent to a sine wave right at the origin, this line right here would have a slope of 1 unit. Now notice that as the graph goes from 0 to pi over 2, notice that the graph is getting shallower. So we would expect that the slopes would be smaller than 1. So the next one I've asked is pi over 4. Pi over 4 is halfway between 0 and pi over 2, or in other words, 45 degrees. So that would just be f prime at pi over 4 would just be the cos of pi over 4. If you enter the cos of pi over 4 on your calculator in decimal form, it's approximately 0.7071. In exact form, it's root 2 over 2. Notice that the 0.7071 seems to make sense with what we talked about. 45 degrees right here, we would expect that the tangent would not be quite as steep as it was at the origin, and in fact, it's reduced to 0.7071. So it's interesting that as you travel along a sine wave, the slope of the tangent is going to be the cos value of that particular angle. It's kind of an interesting fact of trig functions. So right here at pi over 2, before we even do the derivative, pi over 2 seems to be a peak on this graph, so we would expect that the tangent line would have a slope of 0. So f prime at pi over 2 is just going to be the cos of pi over 2, which indeed gives us 0. And for the last one I asked was pi. If you were over here, which would be the mirror image of this point, and you drew a tangent, think about what you would expect the slope to be. The curve is doing exactly the same thing at pi as it was doing at 0, except this time it's on its way down. So if we took f prime at pi, it would be the cos value of pi, and the cos of pi is -1. So I thought I'd just take you through this example so you get a feeling for what actually you found. The derivative of a sine wave is just the cos value of the angle at the point you're interested in. Now before we do any more complicated derivatives, you may recall that when we did logs and exponents, we had to deal with the argument situation. So I'd like to give you an extended rule of what we just learned. We learned that the derivative of sine is cos. If you have a function f of x that's equal to sine u, where u is a function of x. In other words, what if the argument, the part right here inside the trig function, what if the argument isn't just an x? What if it's a function of its own right? Then, of course, according to the chain rule, then what we're going to have to do is when we take the derivative f prime, we will just get the cos of u, whatever the argument is, but then we have to multiply by the derivative of u with respect to x. This hopefully makes some sense to you since we saw the same thing with the logs and exponents. So the argument never changes, but you always have to take the derivative of the argument. So let's just do a few examples. So if I gave you a function like f of x equals, forgot to put the sign in there. Suppose I gave you the function f of x equals sine 10x. I'm sorry for the mess there, but that's supposed to be the sine of 10x. Then when you take the derivative f prime, according to this rule, you start out by, if you have a sine function, the derivative is cos. And you notice that the argument stays the same. So this is just going to be the cos of 10x. So in other words, the rule is the same as this rule here. If you have the sine of an angle, the derivative is the cos of the angle. But because of the chain rule, we have to multiply by the derivative of the argument. The argument in this case is 10x, which would have a derivative of 10. And if you want to, it makes more sense to put that 10 in front so that it's not confusing with the argument. So the proper way to write that would be 10 cos 10x. So with this extended rule here, we now are able to take the derivative of sine of any argument that we want. So another example would be something like the function f of x equals the sine of 3x squared plus 5x plus 1. All you have to remember is that the argument never changes. If you have an argument of 3x squared plus 5x plus 1, then your derivative f prime is going to be the cos of 3x squared plus 5x plus 1. But then something that's very important to remember, of course, is you must always take the derivative of the argument. So all of this would get multiplied by 6x plus 5. Now, it's not wrong to leave the 6x plus 5 at the end. The only potential difficulty there is someone looking at this might think that you're taking the cos of all of this. But you're only taking the cos of the argument, and then you're multiplying the result by 6x plus 5. So it's often a good idea to write the 6x plus 5 in front of the cos function. Obviously, the rules that we've studied earlier also apply. So if you had something like y equals 2x sine x. So now we've got a product of two functions. We have a linear function 2x being multiplied by the trig function sine x. So the derivative dy dx would be the derivative of 2x, which is 2, times sine x, plus the derivative of sine x, which is cos x, times 2x. We can combine some of the rules we learned in the previous section with logs and exponents. We could have y equals e to the sine 3x. So a person does have to always keep in mind that to not forget the rules that we've learned previously. This is the natural exponential function, and you may recall that the derivative of that is itself. So the derivative dy dx would just be e to the sine 3x. But the argument in this case, the argument is sine 3x. So using the chain rule, after you take the derivative of e to the sine 3x, you have to take the derivative of the argument. So this is going to get multiplied by the derivative of sine 3x, which is cos 3x. But then you got to keep unraveling the layers. Now you have to move inside and take the derivative of the argument 3x, and so times 3. And the last example I want to do is just sort of a clarification to make sure you understand what this means. So in our last example, what if we had y equals sine squared x? Now in trigonometry, when we square a trig function, we always write the squared in between the sine and the x. But you understand that that really just means the sine of x all squared. Now that I've written it that way, it might be more obvious to how we're going to take the derivative. We have a function raised to a power. It's our extended power rule. So the derivative dy dx, you would take the power, multiply it out front, subtract 1 from the exponent, times the derivative of what's inside the bracket, which would just be cos x, times the derivative of the argument of sine x, but because it's just x, that would be a 1, and we're finished. And then just to make things more complicated, often in trigonometry, I can't overstate the importance of identities. You'll notice the answer we have here. The answer is 2 sine x cos x. If you look at an identity sheet, you'll find that identity on there. Often in trigonometry, we can use using identities. 2 sine x cos x is called a double angle identity. So you'll often see the answer written as sine 2x. That does create a bit of confusion for people because you'll get an answer and you'll wonder whether it's the right answer because the book will have the answer maybe written as sine 2x. So you just have to always be aware in trig that identities can often be used to do the simplifying. So now that we've developed the derivative of sine x, we can turn our attention to the function cos x. And the good news is that it took a while to develop the derivative of sine x because we had to go back to our definition of a derivative. But every other trig function, all 6 of them, well, all 5 of them except for sine, can be written in terms of sine or cos. And so what we're going to do here is we're going to develop the derivative of cos x, but it's not going to take nearly the effort it did to develop the derivative of sine x. So first of all, let's draw a picture of cos x just so we're familiar with what the graph looks like. Cos x, if you traveled around the unit circle again, cos is the x value as you travel around. So when you start here at 0 rads, your x value is already 1. So your cos is starting off at 1, and then as you proceed up to pi over 2, the value of x gets shorter until finally at pi over 2, the value of x is 0. So what a cos graph does is it starts at 1. It just does the opposite of sine. Sine starts at 0 and climbs to 1. Cos starts at 1 and falls to 0. And then when you move into quadrant 2, your x's become negative. So the cos wave turns around and eventually hits -1 over here at pi, and then travels back up to 0 as you travel around to 270 or 3 pi over 2, and finishes off again at the end of your trip around the circle, right where it started at a value of 1. So that would be your picture of a cos wave. And to develop the derivative of the cos function, you need to appreciate that cos, if you look at the word cosine, notice that it's really just the word sine with a co in front. Cosine is called it's the complementary function of sine. That's what the cos stands for. It's the complementary function of sine. And complementary in geometry means 2 angles that add up to 90. So something that you probably understand, but if you don't, I'd like to explain to you that if you take the cos of some angle like 20 degrees, it'll have exactly the same value as the sine of its complement. So if you take the cos of 20, it'll be the same answer as the sine of 70. Or if you take the cos of 45 degrees, cos of 45 is equal to the sine of 45. That's the only angle in the first quadrant where sine and cos are equal to each other. Your cos wave falls from 1 to 0. Your sine wave climbs from 0 to pi over 2. And they would cross at 45 degrees, which would be the value of cos 45 and sine 45. So what if we extended that to the general case? What if we wanted to just have the cos of x? Well, the cos of x is just going to be the sine of pi over 2 minus x. Just 90 degrees subtract the x value. So our goal here is to find the derivative of cos x. So we want to find the derivative of f of x equals cos x. Well, we don't have a rule for that, but we do have a rule for sine. So why not write this function as f of x equals the sine of pi over 2 minus x? Because those are equivalent functions. That's what cosine is. It's just the complement of sine. Now we can take the derivative. The derivative f prime, if you have the sign of an argument, the derivative says that you take the cos of the argument, but then you have to always multiply by the derivative of the argument. Well, pi over 2 is a constant, so it has a derivative of 0, and negative x would just have a derivative of -1. Now, it'd be nice to write our final answer without the pi over 2 minus x. So if you think about it, if cos x is sine 90 minus x, then what is cos 90 minus x? Well, that's just the sine of x. And so we end up with f prime of x equals, the negative comes out front, and we just get negative sine x. And there's our second derivative of trigonometry. We've just established the fact that, so here's our rule, if we have a function f of x that's equal to cos x, then the derivative f prime is just the negative of sine x. You notice that the two rules are very simple to remember, the only problem being the negative sign. The derivative of sine is cos, the derivative of cos is sine, except the cos has a negative in the answer. So you just want to make sure you keep those straight. But it's an interesting fact that both sine and cosine waves have each other as their derivatives. Now, if the argument isn't x, if it's a function of x, then the same rule applies that we saw with sine, and it'll be the same rule that applies for all the trig functions. So just to finish this up, if you had a function f of x that was equal to cos u, where u is a function of x, then the derivative f prime will be negative sine u times du dx. So we'll just do a couple. I mean, it's exactly the same as you did with sine, so we don't need to go over too much of this. But just so you get a feeling for working with cos, we'll do a couple of examples here. So if you had something like y equals cos 5x, and we want to take the derivative. Well, the derivative would just be dy dx equals, and then you would take the derivative of cos 5x, which is just negative sine 5x, but then you always have to multiply by the derivative of the argument. So your answer would be negative 5 sine 5x. If you practice the sine function and make sure you have that under control, then the cos function, the work is exactly the same. So I'm not going to do too many more of these. Maybe as another one we can try something like f of x equals the natural log of the cos of x. You can and often do have functions that combine different transcendental functions. Here we have a natural logarithm of a trig function. So the derivative f prime, well, the derivative of the natural log of x is 1 over the argument being what's inside the log function. So this is going to be 1 over cos x times the derivative of the argument, which would be negative sine x. And you know I mentioned earlier that often these answers can be simplified with identities. Well, here's another example. We now have negative sine over cos, which is an identity, which is tan. So just be careful with that, because often answers can be simplified using identities. And maybe we'll just do one more example. There's really not much else I can show you. It's just a matter of understanding really the concept of the argument. So what if we had y equals 4 cos x squared? And the reason why I thought I'd do this example is don't confuse cos x squared with cos x all squared. There's a huge difference between cos x squared and cos squared x. In the first one, you're squaring the angle and then taking the cos. In the second one, you're taking the cos of the angle and then squaring the result. So in this case, the argument is the x squared. So our derivative, dy dx, would equal, the 4 is just a constant, so it would just stay out front. Then we would take the derivative of cos x squared, which would be negative sine x squared. And then, of course, we have to multiply by the derivative of the argument. And then if you wanted to just write that a little bit simpler, we could combine all the constants out front and just go negative 8 sine x squared. So now we've seen that we can take the derivative of our two basic trig functions, sine and cos. What I'd like to do to finish off this section now is keep in mind that throughout this course we've been doing applications. Every time we learned how to, back in chapter 4 we learned our rules of differentiation, and then we turned our attention to the different applications of calculus, curve sketching, related rate problems, optimization problems, and so on. Well, the same thing applies to this unit. We still have to be able to handle the application questions. So I'm going to finish off with a handful of examples here, just to remind you of some of the stuff we've done earlier in this class. What we have here is a function that you may recall is called implicit. The function is not y as a function of x. If you have y equals a function of x, it's called an explicit function. If the y is not isolated, it's called implicit. So we have to use a technique called implicit differentiation. So what we're doing here is we want to find the derivative of y with respect to x. There are three terms. We have to take the derivative of every term in this expression with respect to x. If you take the derivative of x squared is a function of x. So the derivative of x squared with respect to x is just 2x. But if you try taking the derivative of sine y is not a function of x. It's a function of y. So what you have to do is first of all take the derivative with respect to y, which would be cos y. But then you may recall I called it the compensating term. You have to multiply by a term that gives you what you want because of the chain rule. So we have to multiply by dy dx. If you forget why that dy dx is there, you might have to go back and have a look at the topic called implicit differentiation. Now we have to also take the derivative of the other side, but of course that's a constant. So we're just going to get 0. Now once you've differentiated implicitly, there's another step involved in this process, and that is you have to isolate the dy dx. So you have to now rearrange this expression to get the dy dx by itself. So we're going to have cos y dy dx equals negative 2x. We can divide both sides by cos, and we end up with negative 2x over cos y. And that would be our answer. Now, you're going to think I'm just repeating myself an awful lot here, but once again, we could use an identity. If you'd rather not have the cos on the denominator, cos is just the reciprocal of secant. So what we could do is we could write the answer 2x secant y. Now, it's not necessary to do that, but again, just so you know, it's almost always possible to simplify an answer in trig using some kind of identity. Another application that we spent some time on was the curve sketching, where we had to find extreme values. So I'd like to do an example that says, find the local extrema, the max-min values, of the function f of x equals 2 cos x plus x. Now the function 2 cos x plus x is a cos wave that's been added to a linear function. So the graph would go on forever. So in these questions, we often just restrict ourselves to an interval. So in this case, we just want to examine this graph between 0 and 2 pi, and we want to know what are the extreme values, what are the local max-min values. So you may recall that your local max-min values are going to occur wherever your derivative is 0. They're called critical points, or wherever the derivative doesn't exist. So what we're going to do here is we're going to take the derivative f prime, the derivative of 2 cos x. Well, 2 is a constant, and the derivative of cos is negative sine. So this is going to be negative 2 sine x plus the derivative of x, which is 1. So there's our derivative, but we're interested in what are called the critical points. So the critical points are wherever the derivative is equal to 0 or the derivative is undefined. Now this derivative is never undefined. There's no restrictions on the domain of x, but we can solve it equal to 0. So we can move the 1, divide by negative 2, and we get sine x equals 1/2. Now at this point you have to know how to solve a trig equation. And to solve a trig equation, what you need to do is isolate the x. You can't divide by sine. This sine is not being multiplied. It's a function. So you have to do what's called the inverse sine. So x is going to be sine negative 1/2. Now if you type that into your calculator, and again, you should be in rads, you're going to get probably a decimal, unless you have a newer version of a calculator that gives the exact answer. We sure prefer to work with the exact answer, so you might want to consider purchasing one of those calculators if you don't have one. But it turns out that the answer would be pi over 6. But you have to understand trig a little bit more than just using your calculator. If you travel around a unit circle from 0 to 2 pi, so if you travel all the way around from 0 to 2 pi, you are going to encounter more than just one angle that has a sine of 1/2. Sine is going to be 1/2 over here in quadrant 1, You're going to have a y value of a half, but you're also going to have a y value of a half over in quadrant 2. You may know something called the cast rule that could help you with that. So the pi over 6 is called the principal angle or the main angle, but there's actually a second angle, and that angle would be over here in quadrant 2, where the reference angle is also pi over 6. So there's actually going to be two answers, pi over 6 and 5 pi over 6. You can verify that on your calculator. If you enter the sign of pi over 6 on your calculator, you will get a half. And if you enter the sign of 5 pi over 6 on your calculator, you will also get a half. If you were to go down here in quadrants 3 and 4, you would get negative a half for the same reference angle. So if you tried the sign of, let's say, 7 pi over 6, which would be 210, you'll get negative 1 half, or same with 11 pi over 6. Now the question wanted us to find the local extrema. So we know we have an extreme value at pi over 6 and 5 pi over 6. If we wanted to actually classify them as whether they're max or mins, you may recall we learned something called the second derivative test. The second derivative test says, so we take the second derivative f double prime. If you take the derivative again, we're going to get negative 2 times the derivative of sine, which is cos. The second derivative test says that if you plug your critical points in, if you get a negative answer, you have a local max, and if you have a positive answer, you have a local min. So all I need to do now is plug in my two critical values. So f double prime at pi over 6. Now you can use a calculator, or if you just understand a little bit about trig, pi over 6 is in quadrant 1. So the cos of pi over 6 is going to be a positive answer because we're in quadrant 1. So this is going to be a positive answer times a negative 2. So this is going to give us a negative value. You can always just use a calculator. Because it's a negative value, we can make the conclusion that pi over 6 is a local max. So our curve has a peak at pi over 6. If we now find f double prime at 5 pi over 6, we'll get negative 2 times the cos of 5 pi over 6. 5 pi over 6 is in quadrant 2. Cos of an angle in quadrant 2 is negative times a negative, and we're going to get a positive answer. And that tells us that we have 5 pi over 6 would be a local min value. Okay, so we'll just do we'll do one more example. So I've shown you an implicit differentiation question. We've done a curve sketching, and let's finish things off with a related rate problem. So earlier in this course, we studied a category of problems called related rate. And if you recall, there were problems when things were changing with time. Well, obviously, what can also be changing with time are angles. So what I've done here is I've written down a word problem we're going to work through together in which a ladder is sliding down a vertical wall. And the question is asking us, at what rate does the angle of elevation change at a particular moment in this situation? So first of all, let's draw a picture of what's happening here. We have a ladder leaning against the wall. The ladder is 5 meters long, so the ladder is a constant. We don't need to assign a variable to it. The wall is vertical, so we can assume that this is a right angle. And now, the first thing you do in a related rate problem is you assign variables to things that are changing. So as the ladder slides down the wall, we're told how fast that happens. It has a downward velocity of 0.5 meters a second. So the ladder, this is the top of the ladder. This part of the ladder is sliding down the wall. So this piece right here, the height that the ladder is above the ground, is changing with time. And we are given that rate. We are told that dx dt is negative 1/2. It's negative because it's decreasing. So that's our given rate of change. And then the question says, find the rate at which the angle of elevation. The angle of elevation is the angle that the ladder makes with the horizontal. So the angle of elevation, we'll call it theta. That's what the question wants us to find. It wants us to find d theta dt, the rate of change of the angle with time, when the ladder is 3 meters above the ground. So when x is 3. So this is how you set up a related rate problem. You identify, usually with a picture, your variables, and then you usually will have a given rate of change. Well, you'll always have a given rate of change, and then you'll be asked to find a rate of change. And everything here is with respect to time. Now the next step is you have to write a function that relates the variables in your question. So you have to ask yourself, how are theta and x related? Well, we have a right triangle, and we can use SOHCAHTOA. We know that if you have an angle called theta, this is the opposite side and this is the hypotenuse. So we have a function called sine. We know that the sine of theta will equal x over 5. That's just a definition of sine, opposite over hypotenuse. Once we've got our function, we're free to differentiate it. Now remember that in a related rate problem, you're differentiating with respect to time. So everything is the chain rule. So we take the derivative of sine theta, which is cos theta, but we have to multiply by our compensating term, which would be d theta dt, equals, now x over 5 is the same thing as 1/5 x. So the derivative of 1/5 x would just be 1/5 dx dt. Remember that you always have to put the compensating term because of the chain rule. Okay, so there's our differentiated function. Now we just need to plug in the values that are necessary to solve. We're trying to solve for d theta dt. So to do that, we need to know two things. We need to know dx dt, which we do know is -1/2. But you notice that we need to know the cos of theta. So at the moment that the ladder is sliding down the wall, so this is what's happening, is that our ladder has slid down so that it is 3 meters above the ground. And the question tells us that we need to know the cos of theta. Well, the cos of theta is adjacent over hypotenuse. So this piece right here, which we can just call y, we need to know that value so that we can find the cos of theta. Now you may recognize the triangle, and if it's a Pythagorean, they're called Pythagorean triplets, where all the values are whole numbers. If you don't recognize it, you can just do 3 squared plus y squared equals 5 squared. But y will turn out to be 4. It's a 3, 4, 5 triangle. So the cos of theta is 4/5. Notice that we don't have to actually find theta. We just need to know the cos of theta in our differentiated function. So the cos of theta, at the moment we're solving the problem, is 4/5 times d theta dt equals 1/5 times -1/2. So to solve for d theta dt, we're going to have 1/5 times -1/2, which is -1/10, times, when you divide by 4/5, you multiply by 5/4, which will give us -5 over 40, or -1/8. Now of interest here are what are our units. All of the numbers in this question are in meters. And you'll notice that there's meters on both sides, so they're going to cancel. So what we end up with is a real number, which again is the significance of rads. It would not be correct to call this a degree. There are no degrees anywhere in our calculations. This answer is just a real number. So the units would be the change in an angle in a real number unit, which is a rad, per our unit time, which in this case is seconds. So at the moment that the ladder is 3 meters above the ground, this angle right here, theta, is decreasing at a rate of 1/8 of a rad per second. Okay, so that wraps up section 6.4. In the next section, we're going to investigate the other 4 secondary trig ratios.